Assalamualaikum warahmatullahi wabarakatuh. Today we'll be presenting industrial wastewater treatment design proposal from palm oil mill effluent. And we are from group 2 and in this table listed our group member.
Hi and Assalamualaikum. My name is Nur Fadila, matric ID KA21065. So today I will present about introduction to the assigned industry, which is palm oil mill effluent. So first is massive wastewater generation. So the production of palm oil use wet extraction method, consuming 5 to 7.5 tons of water for every single tons of oil produced. So this result in a massive volume of heavily polluted wastewater, which is POME. So next is the POME characteristic. That characteristic it contain no added chemical toxin or heavy metal because the extraction was purely mechanical actually. However, it's densely packed with natural organic matter, fat, and suspended solid. So next is the three specific production source, which is 60% from clarification wastewater, 36% from sterilizer condensed from stream processing, and 4% from hydrocyclone separation waste. And last is the severe properties and environmental treat of POME. So the freshly discharged raw POME is very hot, like 80 to 90 degrees Celsius, and also highly acidic, so it's not safe. And it also will, the impact is strip oxygen from river, block sunlight, coat the water surface with oil, and also suffocate the aquatic life.
My name is Aisha Nabila binti Norisham. Today I will present the wastewater characteristic of palm oil mill effluent or POME and compares the raw wastewater quality with the Malaysia Industrial Effluent Standard. POME is a high-strength agro-industrial wastewater generated from palm oil mining process such as sterilization, clarification and hydrocyclone operations. As shown in the table, the raw POME contains extremely high pollutant concentration, including a BOD of 25,000, COD 50,000, TSS of 18,000, oil and grease of 4,000, and the ammonia nitrogen of 80 mg per liter. In Malaysia, industrial wastewater discharge is regulated under two standards, Standard A and Standard B. Standard A is more stringent and applies to discharge into designated water catchment, while Standard B applies to discharge into inland water outside protected catchment area. For this project, both standards were considered during the wastewater characterization on stage. However, Standard B was selected as the design basis because the project specification does not indicate that the discharge point is located within a protected water catchment area. In addition, Standard B is the standard most commonly applied to industrial wastewater, including the palm oil mill effluent. The comparison clearly shows that all raw POME parameters exceed both Standard A and Standard B limits, confirming that the need for an effective treatment system before discharge.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Atira Wadia binti Zulkifli and my matric ID is KA22021. So in this slide, I will explain about the environmental issue caused by POME wastewater. So palm oil mill effluent or POME can cause several environmental problems if it is discharged without proper treatment. So the first issue is oxygen depletion in water body, where high BOD and COD level mean microorganisms consume large amount of dissolved oxygen while decomposing organic matter. This can create oxygen deficient condition leading to fish kill and damage to aquatic ecosystem. The second issue is water pollution caused by suspended solids and oil. High suspended solid increase water turbidity, reducing sunlight penetration and limiting photosynthesis of aquatic plants. At the same time, oil and grease form a layer on the water surface, reducing oxygen transfer and harming aquatic organisms. The third issue is eutrophication and odor generation. Nutrients such as nitrogen can promote excessive algae growth, resulting in algae bloom and further oxygen depletion. In addition, untreated POME undergoes anaerobic decomposition, producing foul-smelling gases such as hydrogen sulfide and methane, which can affect nearby communities and contribute to greenhouse gas emission. That's all from me.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ashraf bin Umar Amin. Now I will talk about the proposed treatment process. So these are the preliminary unit proposed for the POME treatment system. First, a screening unit is proposed to remove large solids such as palm fiber and shell fragment. This helps prevent clogging and protect downstream equipment. Next, a skimming tank is included to remove free oil and grease. Since POME contains a high concentration of oil, this unit reduces the organic load entering the subsequent treatment stages. An equalization tank is then proposed to homogenize fluctuation in flow rate, temperature, and wastewater characteristic. Sodium hydroxide dosing is also applied to adjust the pH closer to neutral, ensuring stable operating condition for the downstream biological treatment process. This section will cover the biological treatment stage of the proposed POME treatment system. First, the anaerobic pond acts as the main gradation unit. It uses anaerobic bacteria to break down the high organic load in POME with the oxygen, producing biogas in the process. This stage is highly efficient, removing around 80 to 90% of the COD and BOD, while also reducing energy requirements since no aeration is needed. Next, the aeration tank further treats the effluent using aerobic bacteria. Oxygen is supplied through mechanical aeration, allowing the remaining organic matter to be degraded. In addition, nitrifying bacteria convert ammonia about 80 mg per liter into less harmful nitrates, improving effluent quality for downstream treatment. After biological treatment, the effluent enters the clarifier, which is a gravity settling tank. Here, suspended biomass and sludge from the aeration tank settle to the bottom due to the high density, while the clarified water overflow from the top. A portion of the settled sludge is recycled back to the aeration tank to maintain microbial activity, while excess sludge is removed for further treatment. Next, the water passes through an activated carbon absorber, which acts as a final polishing step. The granular activated carbon removes remaining organic compound, color, and trace pollutants such as lignin and tannins through absorption. Finally, the treated water is directed to the inspection tank, where microorganisms such as coliform are eliminated before discharge. In this section, I will present the sludge treatment line of the proposed system. First, the sludge thickener concentrates the dilute sludge collected from the clarifier by removing excess water, significantly reducing its volume and improving handling efficiency. Next, the thickened sludge enters the anaerobic digestion tank, where anaerobic bacteria break down organic solid in an oxygen-free environment. This process will stabilize the sludge, reduce odor, and decrease overall waste mass. Finally, the filter press removes remaining water under high pressure, producing dry sludge cake suitable for disposal or reuse, while the filtrate is recycled back to the aeration tank for further treatment.
My name is Wong Liu Tin, matrix ID KA22070. I'll be presenting the process flow diagram and design calculation and sizing. So our proposed treatment system consists of several unit operations arranged in sequence to effectively reduce the pollutant and produce the treated water that meets the environmental discharge requirement. From the process flow diagram, the treatment process consists of screening, oil removal, flow equalization, biological treatment, clarification, absorption, and sludge management unit. First, for the screening unit, we assume that this unit is a rectangular and assume the velocity is 0.3 meter per second. By using this value, we can calculate the area of the screening unit equals to 0.0193 meter cube, and the detention time is at 0.5 seconds, and the length of this unit is 2.55. For the screening tank, we assume that the tank is a rectangular tank, and the SOR equals to 20 meter cube per meter square per day, and the D equals to 3 meter. By using this value, we calculate that the area is equals to 25 meter square and the volume is 75 meter cube. By calculate the oil loading, we got that skimming tank received 1,999.5 kilo oil per day. After the design calculation for the equalizing tank, we know that the volume of the tank is 62.5 meter cube. After add the safety factor 20%, the final volume of the tank is 75 meter cube. Then our target pH value is equal to 7. So 0.6305 kilogram per day of the sodium hydroxide needed to adjust the pH. For the anaerobic pond, 90% of BOD and COD will be removed at this anaerobic pond. After calculation, we know that the volume of each pond is 2,150 meter cube. For the aeration tank, we assume that the target COD equals to 200 mg per L, so that the COD removed per day at this tank is equal to 2,400 kilogram per day. Then our target BOD is equal to 30 mg per L. So that have 1,235 kilogram per day of BOD will be removed per day. Next, I assume that the food to microorganism ratio equals to 0.3. We know that the MLSS mass equals to 4,166.67 kg. By using this value, we can calculate the aeration tank value, which is equal to 1,388.9 meter cube. For the clarifier, we assume that SLR equals to 20 and SWT equals to 3.5 meter, then MLSS equals to 3,000 mg per L. Using this value, we can calculate the volume of the tank, which is equal to 87.5 meter cube, and the real length equals to 17.72 meters. For the activated carbon absorber, the COD inlet is 200 mg per L, and our target is equals to 50 mg per L. So 75 kilogram per day of COD need to be removed. By assume the EBCT equals to 20 minutes and the bed depth equals to 2 meter, we can calculate the volume, which is equal to 6.944 meter cube. For the sludge thickener, by using some assumption, we can calculate that the area equals to 1.67 meter square and the diameter equals to 1.4567 meter. For the anaerobic digester, we assume the HRT equals to 30 days and the digester depth equals to 4 meter. By using this value, we can calculate that the area equals to 37.5 meter square and the volume equals to 150 meter cube. Last, for the filter pass, we assume that this pass is the square filter plate. So after calculation, our length of the filter pass is equal to 1.5811 meter and the area is equal to 2.5 meter square. That's all from me. Thank you.
Starting with the screening unit, the equipment is constructed from carbon steel. Carbon steel is selected because it provides mechanical strength, is durable, and is inexpensive for handling coarse solid materials at the preliminary treatment stage. The estimated cost for the screening unit is approximately 1.52 million ringgit Malaysia, making it the most expensive equipment in the system due to the specialized mechanical screening mechanism. Next is the skimming tank. It's also made from carbon steel, which offers sufficient structural strength and corrosion resistance for separating oil and grease from the wastewater while maintaining a reasonable construction cost. With a design volume of 75 cubic meter, the estimated cost is 339,513 Malaysian ringgit. Similarly, the equalization tank uses carbon steel construction because it is strong, easy to fabricate, and suitable for storing and homogenizing wastewater before biological treatment. Since it has the same design volume as the skimming tank, its estimated cost is 339,513 Malaysian ringgit. Next is for the anaerobic point. The cost estimation mainly consists of land acquisition together with annual operation and maintenance costs instead of equipment fabrication costs. The anaerobic point utilizes natural biological degradation process requiring minimal energy input and low operating costs. The total annual cost is estimated to 32,622 Malaysian ringgit. Move to the aeration tank, where it is constructed from carbon steel, which provide high strength and durability while supporting continuous aeration and biological activity. The estimated economic cost for the aeration tank is 396,599 Malaysian ringgit. Next, the clarifier is also fabricated from carbon steel as the material offers adequate strength for long-term operation under wet conditions while remaining cost-effective. The estimated cost of the clarifier is 349,267 Malaysian ringgit. For the activated carbon absorber, is designed using carbon steel because it provides sufficient structural support for the activated carbon bed and pressure loading while maintaining lower fabrication costs compared to stainless steel. The estimated cost of the unit is 373,766 Malaysian ringgit. Next, for the sludge treatment process, the sludge thickener is constructed from concrete. Concrete is selected because it is highly durable, resistant to corrosion from sludge, and suitable for large stationary settling structure. The estimated cost for the sludge thickener is 581,805 Malaysian ringgit. For the anaerobic digester, use reinforced concrete which provide excellent structural stability and durability for long-term anaerobic digestion while resisting pressure and chemical attack from the sludge. The estimated cost of this unit is 792,241 Malaysian ringgit. And finally, is the filter press. Use polypropylene plates because polypropylene has excellent chemical resistance, high mechanical strength, and it is lightweight, making it suitable for repeated sludge dewatering operation. The estimated cost of the filter press is 158,902 Malaysian ringgit. In conclusion, the total estimated economic cost for the proposed palm oil mill effluent treatment system is approximately 4.89 million Malaysian ringgit. The selected materials provide a balance between durability, corrosion resistance, structural strength, and economic feasibility, ensuring reliable long-term operation of the treatment plant while minimizing maintenance and replacement costs. Next is the land cost estimation for the proposed wastewater treatment based on the total area required for the treatment units using the industrial land price, which is 50 ringgit Malaysian per square foot. The estimated land cost is about 5.3 million Malaysian ringgit. Next, the chemical cost, where the main chemical used in the treatment system is sodium hydroxide or NaO. So the annual cost of chlorine, which is 2,828 per year Malaysian ringgit. Next is operation and maintenance cost, where for operation and maintenance cost, expense include labor, monitoring, assisting, energy consumption, and routine maintenance activity. So the total operating cost is about 32,622 Malaysian ringgit.